and I'll push the record button. And Catherine, you should be able to share your screen with us.
Yeah, let me see if I can do this.
And I'll shut up. And if you have any questions, either type your questions in the chat or raise your hand after the talk, or just tell me that you want to speak.
You're seeing the wrong one, I think, yeah?
Yes, we see the presenters mode.
Bene. It's, sorry. PowerPoint goes a bit funny on my two screens. I apologize. Should have practiced that before, huh?
Now we see a word. Now it's perfect.
Hopefully. Okay, so firstly, thank you, Christoph, for inviting me, and also to Richard, who couldn't make it today. I feel a little bit like an outsider, but hopefully I can get you a bit enthused about sediments as well. And so just to give you a bit of background, in 2013, I took my first trip to Central Asia. And at the time I was working in Leipzig, and I was working in a human evolution department. And so my focus at the time was on finding and dating evidence of human traces along the Tian Shan Piedmont, specifically in Kazakhstan. But I'm a geologist, and as a geologist, I was really in awe of the amazing diversity of sediment deposits and landforms which you find in between the mountains and the steppe to the north of Lake Balkhash. So I started plotting my next project to start investigating these sedimentary deposits in more depth. And I got lucky, and towards the end of 2016, I took up a new position as an independent group leader at the Max Planck Institute for Chemistry in Mainz. And I started a 5-year project, which was working on scientific problems relating to long-term climate change in Kazakhstan and in Tajikistan. And I was also excited because I was able to start getting involved in some of the new geological proxy approaches for reconstructing past climates in a quantitative sort of manner. And this is something which we hadn't done before. So late last year, I started my new position here in Tübingen, and the discoveries of my Mainz group are in the process of being published. Some of them have come out and some of them are still in press, and I'll discuss some of those today. So I'd like to share some of my discoveries from my work in Central Asia with you today. And I know that these have less to do with earthquakes and more to do with sediments along the Piedmont, which is being created by that tectonic activity. But I still hope, nevertheless, to win you over a little bit with some of these spectacular landscapes and some of the equally fascinating insights that we can extract from these sorts of landscapes. So my group was set up with the aim of developing quantitative reconstruction of long-term climatic change in the center of the world's largest and most populous continent on Earth. So that's Eurasia. So to provide you with a couple of motivations for working on this particular problem, I'll just give you a little bit of background. So you all know that we're living in times of accelerated climate change globally. So to give you some idea of just how quickly that climate is changing, here are some NASA observations of temperature change, and in the top left. And this shows the observed temperature increase from 1951 to 1980 versus 2013 to 2017 years. And what we can see here is that there are some really strong, stark hotspots, mostly on land and especially over Eurasia. And then if we look at the graph on, or the map on the bottom right, we can see from the IPCC report indicators of drought severity over the last century or so. And the brown areas are highlighting areas where we've got increases in severity of droughts. And again, we've got hotspots on the dryland margins mostly, so particularly in the Sahel, but also in Central Asia. So under these conditions of accelerated global climate change, conditions in these marginal regions, like the edges of deserts, are going to become increasingly unstable and unable to support human populations. And since the world's drylands occupy about 50% of the world's landmass and host about 40% of the world's people, this increasing instability is going to become a central concern for the future. So my motivation as a sedimentologist working in dryland regions was validated by this model from a few years ago, which indicates that the world's drylands and the area taken up by drylands is going to expand in the coming decades. And I'd like again to draw your attention across to Central Asia, where we can see very large areas of the Eurasian steppe and the Central Asian deserts are set to expand and intensify in aridity in the coming decades. So in order to understand what the future might hold for us, we also need to understand the nature of landscape change. We need to understand what kinds of landscapes are possible, what sorts of landscapes have been inherited from past conditions. So we know that climates and environments have changed to varying degrees over different timescales. So in the present day, we know that there are climate variations which are greatest between summer and winter. But in order to understand future change, we need to look over longer timescales. And over the last few million years, the climate has oscillated between ice ages and interglacials, these warmer phases. And these changes were much more extreme than what we see in the seasonal changes that we observe in the present day. So what I'd like to show you here are two maps which give us an indication of what the environment looked like in the past compared with the present day. Now, if we rewind to the last ice age about 20,000 years ago, you'll see not only that we've got vastly expanded ice sheets, we also have vastly expanded desert areas. In addition to that, we've got colder conditions, but the conditions were also drier and they were also windier. So what that meant was that we had a lot of dust blowing around in the atmosphere. Now, this dust accumulates on the continents where it forms very thick packages of sediment known as loess. So what do we know about the Earth's past climate? So if we take a look at the last full glacial cycle, so this is encompasses the last interglacial phase, about 120,000 years ago, the intervening glacial period and the last glacial maximum, and into the present day interglacial, known as the Holocene. So as a framework, we use the marine oxygen isotope stack. But we have also additional archives from ice cores. And the ice cores, for example, contain small bubbles which have carbon dioxide preserved within those bubbles. And we can get an indication of the atmospheric CO2 concentrations through time. Now, of course, what this tells us is that during the last glacial maximum, conditions were colder, had lower atmospheric CO2, and during the interglacials, the opposite was the case. Now, we can also look at other pieces of information. Now, in particular, I'd like to draw your attention to dust flux. Now, the information that we have about past dust flux, or the best information that we have, is actually coming from things like the Antarctic ice cores. We can actually measure the concentration of dust which is coming into the Antarctic ice. We can also look at marine cores to give us information about how much dust was flying around in the atmosphere. So we can look at the iron flux, which is accumulating in the oceans. And this gives us information about dust-borne iron fertilization in the oceans and the increased production of organic matter. But ultimately, that dust is actually coming from the land. And Central Asia is sitting right at the very center of that land and is dry. So what I decided to do was to go to the source of that and see what the story in Central Asia is telling us about past climates. Now, Central Asia is lying right at the middle of the Eurasian continent, and it's also sitting at a transition zone between major climate subsystems. So we've got the mid-latitude westerlies, which are acting on this region. We also have polar northerlies, which are associated with the polar jets and with the expansion and contraction of the Siberian high with the seasons. Over long time periods, of course, we also have the influence of the uplift of the high mountains. And this has provided Central Asia with a major rain shadow and has limited the penetration of monsoon rainfall into Central Asia and created those vast deserts, which we've just seen. Now, in addition, draped along the mountain Piedmonts are long archives of aeolian dust, or loess, which provide us with information about climatic change through time. So the research of my group has been focused on using these sedimentary archives to understand Earth surface processes, climate dynamics, and climate change through time. And in doing so, hopefully to provide the missing terrestrial link in our understanding of global climate change, which thus far really is very much focused on the marine and the ice core archives. So one of the major reasons why we know so little about Central Asia's role in global climate dynamics, past and present, is because we've largely overlooked the full potential of these large dust archives, this windblown dust or loess. Now, in Central Asia in particular, we have long vertical sequences of loess, which provide us with a really valuable calendar of climatic change. Dust accumulation intensifies during cold glacial phases, as we just saw, and it decreases and we start to get the formation of soils under milder climates. So what this means is that we start to get a layer cake sort of stratigraphy happening. And this example here from Karamaydan in Tajikistan is a beautiful example of that. So we're interested in the loess because it's widespread across continental Eurasia and it can give us really useful information. The Asian high mountain belts provide the ideal topography both for generating dust in the form of glacial and fluvial outflow, and also for trapping it along the foothills or the Piedmonts. So because we've got these loess paleosol packages which are reflecting those ice age interglacial cycles, with the right kind of site, we can actually already start to read climate through time. So this leads to my key research question is how arid Central Asian environments might have changed through time. And the key piece of information here is coming from sediments. So I'm interested in what aeolian sediments can tell us about wind regimes and climate over various timescales. So my group is interested in providing that missing climatic link from land. The dust is coming from the land and we live on it. And so we're setting out to provide that missing link. And we take a threefold approach. So we're interested in looking at sediments in time and using dating techniques to provide quantitative frameworks for change through time. We're interested in sediments on the move. So what sediment transport processes and their relationship to climate can tell us about past climatic change in this region. And also using a number of new proxies to generate quantitative reconstruction of past climates. And I'll focus today on the Tian Shan Piedmont in southeastern Kazakhstan and far western China. Now, our research is trying to emulate or perhaps even surpass the marine and the ice core records. For that, we need continuous samples. And the only way to do that in this sort of environment where the sediment packages are exposed in massive cliffs is to do it by abseil. So over the last 5 years, we ran 4 field campaigns to Kazakhstan and 2 to Tajikistan. We took more than 1,000 kilograms of sediment samples, and we took with us 600 meters of climbing rope in order to undertake our field research. So if we turn to the first of my research foci, we're interested in looking at sediments through time. Now, the main method that we use is luminescence dating. And we've also been increasingly incorporating Bayesian age models to generate chronological frameworks and also quantitative estimates of sedimentation rates through time. So the weapon of choice, many of you will be familiar with this already. This is luminescence dating. Now, this is an absolute dating technique, which is based on the physical properties of crystalline minerals. Now, natural crystals are imperfect, and they contain within them defects within the crystal lattice. And within these defects, charge can be stored, a little bit like a battery. So when you expose that battery or those crystalline minerals to sunlight or through transport, for example, or to heat, this results in the release of the stored charge, and you end up with a depleted battery. Now, as the mineral grains are then deposited and buried, the ionizing radiation present in the surrounding sediment facilitates the trapping of charge in those defects within the crystal lattice again. Now, the rate at which this charge builds up is proportional to the amount of ionizing radiation which is present. This is one part of our age equation, and this is known as the dose rate. Now, the amount of charge which is built up since burial is measured in the form of photons of light. This is called luminescence. And this is released as the mineral grain is exposed to light in the laboratory situation. So this is our radiation dose to the sediment. So when we've got these two parts of the age equation, we have an age for the last exposure of the sediment to sunlight. Luminescence can be applied to a whole bunch of different situations, basically anywhere there are unconsolidated sediments which have been deposited and buried. Few fast facts, we deal mostly with quartz and feldspar minerals. We can work with single grains of sand, and we can work with aliquots of very fine dust. We can date material from almost 0 years to 500,000 years or more. The uncertainty is about 5 to 10%. And we've sampled a range of different contexts with the project. So if we focus on the Ili Basin or the Lake Balkhash region in southeastern Kazakhstan, Western China, just to give you some context, the Ili River, which is the major river, this rises in the Tian Shan in Western China, and it flows into the terminal Lake Balkhash. In this region, we've got a very strong climatic gradient, not only with temperature, but also with precipitation. Most of it is semi-arid, but we actually have some hyper-arid areas close to Lake Balkhash. And importantly for this, we've got widespread aeolian deposits in the form of both loess and dune deposits. So we've been working to understand what both dune and loess deposits can tell us about environment and climate on a range of spatial and temporal scales. So first step, which I took these samples in my first trip in 2013. We did some initial work on loess profiles along the Kazakh Tian Shan Piedmont. We undertook measurements on quartz and feldspar, found that these mostly lay within error of each other. So this suggests that we've got nice, accurate ages. And I've presented these data as an age versus depth plot. And what we can see is that in an age depth plot, the peaks in loess accumulation are indicated by the steeper parts of the curve. Now, what we generally see within these three sites is that there is a peak during stage 3, which is the period of about 37 to 25,000 years ago. And this was thought to be a warmer and wetter phase. So this was a little bit counterintuitive to find that we had increased dust accumulation to the Tian Shan Piedmont during stage 3. We don't see this in other parts of the world. But then we think about the fact that actually we're looking at the rain shadow. We're looking at a dryland region, which is responding more to moisture availability than to temperature. So what this means is that in the Asian high mountains, very likely we're going to have had expansion of glaciers because we've got increased precipitation during this time. So this expansion of glaciers would then have created the fine-grained sediment, which then blows up onto the Piedmont as loess. Now, we wouldn't have known this without having the dating. And we also have a peak in accumulation during the last glacial maximum. Now, this was a period that we knew was drier and colder. So there was less rainfall, but because we had persistent cold conditions, we had persistent glaciers and production of the fine sediment for the loess. So that was the first step. When I started my group, my PhD student Aditi Davish, who's now my postdoc, started working along the Piedmont, and I gave her what I thought was going to be an easy and a safe component for her luminescence, PhD. And I gave her a bunch of sites along the Tian Shan Piedmont and with the aim of dating these things. But of course, Central Asia is never simple. And Aditi found quite a lot of variability in the timing of loess accumulation along the Piedmont, and we'll look at that in a moment. But we also found quite a bit of evidence for seismic activity as well. So I'm not a structural geologist, but what we certainly saw quite a lot of was fabric, which was developed within the unconsolidated loess sediments, which shows that, the LERS has responded to past and recent seismic activity along the range front. And we saw this at pretty much all of our sites. There's some nice examples here from Remizovka, which is a site in Almaty in southeastern Kazakhstan. I don't know what earthquake is responsible for forming this fabric, but we do know that there is quite a lot of seismicity along the range front here. We also found in southern Tajikistan at the Karamaidan site, also similar sorts of fabric. We found slickensides, and we also know that this particular site was actually created by a series of earthquakes in 1941 and 1943, which displaced an entire wall of LERS downslope. So it could well be that this particular event was responsible for the formation of that fabric. At this stage, we don't know any more than that. I'm kind of hoping that there'll be some bachelor and master students to start working on this, but until then, it remains hypothesis. Now, an example of paleoseismicity, Aditi also observed at a site just southeast of Chilik, known as Malubai. Now, at this site, we have about 6 meters of LERS accumulation, and there's a small angular gravel layer at about 1.2 meters depth. Now, what she saw here was displacement of these gravel layers. So what she saw was actually evidence here for tectonic activity. We saw imbrication of clasts, which suggests that there is very strong movement of the sediment in here, and deformation of the gravel layers. So Aditi undertook dating. She started with the quartz, found that to be saturated, so it was too old. So she undertook post-IR dating of the polymineral fine fraction, looking at the feldspar signal, and found that we can start to constrain the timing of this particular faulting event. So it looks like it took place somewhere during marine isotope stage 6. Precisely when is a little bit more difficult to constrain, but we can start to build an envelope. It's quite a neat little site in terms of, looking at tectonic activity preserved within the LERS, but more than that, we can't really say very much. Now, with her new data sets and a reanalysis of published luminescence age depth data sets, which were filtered for quality, Aditi undertook Bayesian statistical age modeling to get information about an improved precision for the chronological frameworks, as well as accumulation rates and sedimentation rates along the Ili Basin, so along the Kazakh Tian Shan Piedmont, as well as a comparison with the Chinese LERS Plateau. Now, what she found was that there is a lot of spatial inhomogeneity between sites. There is a general convergence of information which suggests that there is a peak in accumulation during this marine isotope stage 3, which I identified previously, as well as during the last glacial maximum. But there is so much inhomogeneity that it looks very much like the accumulation rates are very dependent on the topography in this region. That's not a huge surprise. We're looking at a range front where there's quite a lot of topographic complexity. So I think one thing which I've noticed in the LERS community is that they've been very much focused on individual sites, and I can't answer that. I wasn't expecting a phone call, I apologize. Yeah, so what we're starting to see is that you can't just take one individual site and use that as a representative site for past accumulation rate change. So take-home messages, we can take this idea of sediments in time, and particularly if we start to work with Bayesian statistics to generate age models, we can start to reconstruct sediment flux at individual sites, compare these with other sites, and start to reconstruct the sediment flux along the Tian Shan Piedmont in 4 dimensions. And so we've got a schematic image here, which shows that we can start to look at, the distance away from the range front itself, what that might have had as a role in trapping the sediment, for example. But it also enables us to start moving into sediments on the move and Earth surface processes. So now that we have the chronological frameworks for change, we also need to understand how the sediments, including the dust, record climate. And this involves us understanding how the sediments are transported and where it's actually coming from. If we know where aeolian dust is coming from, this can give us a vector for the transport and connection to the climate systems at various scales. So what we've been doing is looking at modern wind regimes and sediment transport. And we've been looking at surface winds, which influence the coarser grained sediment deposits like dunes, which are quite common. And we've been mapping the dunes and pairing these with climate reanalysis to get an indication of how the dunes might be responding to climate. And then we've also been looking at air parcel transport at altitude to give us an idea of the finer grained dust transport pathways. Secondly, we've been also working towards developing a new method for provenancing, so identifying the source of the sediment based on trap charge physics. So that's why I went into so much detail when I was describing luminescence a moment ago. Now, there are some hypotheses for how loess formation works in the Central Asian Piedmont. This was done and perfected by the Soviets in the 20th century. Now, these models assume that glacial activity and desert activity and Piedmont loess processes are all happening at around about the same time. So what we've been doing is trying to test that hypothesis in a more concrete sort of way using geological as well as climate modeling approaches. So if we look at the widespread dunes of southeastern Kazakhstan, which you can see shown in the top right in yellow, I undertook some work with a master's student, Maika Novatsky, who's now a PhD student in Oxford. She undertook some luminescence dating of the dunes and found them to be recently active. So what that suggests is that maybe we can start to use dune morphology to give us information about wind regimes. So to that end, we undertook some climate reanalysis using the data set from the European Centre for Medium Range Weather Forecasting. And we looked at surface wind seasonality and surface wind speeds, which you can see with the wind roses shown on the left and on the right. Now, in addition, Maika also undertook some semi-automated mapping of dune morphology using the Sentinel satellite imagery and open source software. The paper is in preparation, it's nearly out. And we compared then the wind regime analysis with what we saw of the dune morphology. Now, if we take this example from the Talkum area, so just to the south of the Balkhash Delta as an example, and what we can see is that we have persistent northerly wind transport, but the strongest winds are actually coming from the west. What we see from the dunes is that there is both a north-south and an east-west orientation for the dunes. The next question is, where is the sediment actually coming from? Very likely the sediment is coming from the Ili River, which transports a great deal of sediment compared with the Kurti River, which doesn't actually flow most of the time at this point. So what it looks like is that this persistent wind, which is coming from the north, is actually providing us with our sediment supply, but the dune orientation, particularly that east-west dune orientation, is actually being driven by the stronger winds, by the westerly winds. So this is a problem which we're still exploring, understanding how morphology of aeolian features like dunes can give us information about climates, and then we can start taking it further back in time when we start looking at older dune fields. Watch this space. So if we then take a look at some higher altitude dust transport, we're interested in looking at the links here between loess and climate circulation, because the loess itself is being transported not just by surface winds, but also by the higher altitude air masses, which are linked to the larger scale climate systems. So here we did some Lagrangian modeling, looking at the likelihood of air mass and particle origins transported to the small point here at Almaty. And for for those of you who may have some experience with this, we looked at the 20 micron fraction, and we were looking at the 200-meter altitude, coupled with climate reanalysis. Now, the brighter colors correspond to the dominance of the source or the origin of the material which is arriving in Almaty, and the cooler colors are less likely to be coming. So what we see is that local transport is dominating for this particular grain size. We have a very strong westerly component, particularly in the winter. And we do also have a seasonal, we have a bright north-south shading here, which suggests that we've got seasonal northerly transport in the spring. Now, this makes sense because this is also the time when the polar front is actually moving northwards and southwards in these transitional months in the spring and the autumn. And what we can then do is use this information where the material is likely to be coming from to start looking at provenance, where our sediment itself is coming from. So this is using a new method, which is using the characteristics of the source rocks to fingerprint the sedimentary deposits to provide us with a vector for the sediment transport. And again, here we're looking at the southeastern Kazakh Tian Shan loess, and the reason for this is because it's a spectacular natural laboratory which has a number of rivers which are flowing directly down off the Tian Shan, which are all draining different kinds of rock types. And in addition to that, we've also done our climate reanalysis, which suggests that, we've got material coming from the north and from the west, as well as potentially from local katabatic winds. Now, if you remember that luminescence dating is based on the principle of charge, which is trapped within the defects in the crystal lattice. Now, some of these defects are known as Frenkel-Schottky pairs. Now, these relate to different geometries in the molecular linkages of quartz. So the formation of certain defect types within the quartz, known as E prime, appear to increase in frequency with the age of a rock. So we can measure this with electron spin resonance. Now, this is a related technique to luminescence, and it can also be used for dating. And so the idea is that if you've got 3 potential rock sources of each of different age, you'll start to see 3 different E prime signals in the quartz electron spin resonance signal. And then if we can locate the source relative to the deposit, the end deposit, this provides us with a vector for sediment transport and links to sediment atmospheric circulation. So work by Aditi and myself and some colleagues, we worked on comparing the E prime intensity of loess sediments from the Tian Shan Piedmont in Kazakhstan compared with loess from Karamaidan in southern Tajikistan. Now, we know that the rocks of the Kazakh part of the Tian Shan Mountains are older than those of the Zarafshan Mountains, which are likely to be providing the source material from the loess in Tajikistan. And what we were kind of hoping for and observed was that we have a higher intensity of the E prime signal in these Kazakh loess sediments. So this stuff which is derived from much older rocks. So what this suggests is that our method is starting to work. Now, since it's showing some promise, we then decided to test it in our natural laboratory in southeastern Kazakhstan. So we compared a range of different potential source areas, so rocks as well as loose sediments in the Ili-Balkhash Basin, and we compared this with surface loess along the Kazakh Tian Shan Piedmont. So if you remember from the Lagrangian flex part modeling, which we did, it looks that, like, most likely we've got quite a lot of local transports of material, but we also have a component from the westerlies and a component from the northerly winds. Therefore, we analysed samples from those regions, and what we found was that the similarity in the E prime intensity is quite close with samples from close by. So it looks like we've got that local sediment transfer. But then we also have quite a lot of similarities from regions in Area 4, which is to the west, and a couple of samples from Area 3, which is to the north of our area. So it seems to, what we're seeing in the quartz E prime intensity appears to match the models for the dust trajectories, which we did just before. So it's a work in progress, and we're expanding on this using more established techniques, for example, radiogenic isotope provenancing of the same samples. So all I can say is watch this space. But I think we may have a new technique for working out where sediments come from. And that means that it's not just, loess, we can also be looking at where sediments are coming from wherever there are unconsolidated sediments cycling through the system. So ultimately, we're interested in seeing how sediment sources may have changed through time, and in order to get an insight into changes in atmospheric circulation through time. And so here, we're looking at the Karamaidan section in Tajikistan, which I showed you before. It's a nice layer cake. And we looked at changes in the E prime signal down part of the Karamaidan profile in Tajikistan. So from the magnetic analyses and from stratigraphy, we know that the sequence spans about 300 to 800,000 years ago, and therefore about 6 glacial interglacial cycles. So what we can see on the left is variability in the stable oxygen isotope curve from the global marine stack. And we can also see changes in magnetic susceptibility as it alternates between soils and primary loess. Now on the right, we see the changes in E prime intensity down the profile. And what we observe is an inverse correlation between E prime intensity and soil formation in loess. So if we then tease this out in a different way, the graph at the top right shows us the differences between the loess, shown in yellow, and soil horizons, which are shown in brown and orange. So what we think we see here in this case is a change in source, and therefore also a change in wind regime between the glacials and the interglacial phases. So again, it's a new technique. It's something which shows a great deal of promise. And yeah, all I can say is watch this space. So take-home messages from this, we can start to integrate different earth science techniques. So we can use GIS and cartography combined with climate reanalysis and dust trajectory reanalysis to give us an idea of the role of surface and high altitude winds in the morphology and the accumulation of sediments in aeolian systems. Also, our new quartz-based trap charge method for sediment provenance is really exciting. Quartz is, after all, one of the most ubiquitous minerals in terrestrial sediments. And if this works, it can not only give us information about dust transport pathways and climate circulation through time and through space, we can also potentially look at anywhere where sediments are on the move. And it goes well beyond, it's completely independent of the saturation characteristics of the dating limitations. We can look at much, much older material as well. So finally, we also have been interested in looking at how sediments can preserve quantitative parameters of climate in the past. So we've looked now at transported sediments, but what we're also looking at is in situ sediment traces. So we've been looking at stable and clocked isotopes, at lipid biomarkers, and at paleoecology, so pollen and phytoliths, to give us information about how the loess environment climate may have changed through time. So if we go back briefly to our overview of the climate situation over Central Asia, we're in the zone where we've got the winter polar fronts shifting north and south, and this has a bearing on the intensification of the Siberian high and the westerlies over various parts of Central Asia. So it's a sensitive transitional region, has very few records and even fewer which are actually long records. So we don't actually know very much about climatic history or the role of global climate system over Central Eurasia very much at all. Now, I mentioned before that there was a link between loess and glacial conditions. So the stratigraphies of the Central Asian loess are in a really unique position to record the penetration of mid-latitude westerly airflow, which originates in the North Atlantic. So there is a connection between Central Asia and the North Atlantic, thousands of kilometers away. Now, we've got a hypothesis here that the intensity and the degree of spatial penetration of the westerlies would be documented in the Central Asian loess, because this is the area where the westerlies basically fetch up onto the Asian high mountains and start to peter out. So according to this figure here, we've got a mechanism whereby evaporation over the North Atlantic in warmer phases is transported by the westerlies over to arid Central Asia, and this then means that we've got more moisture available. That compresses the moisture up against the mountains of Central Asia and results in the expansion of glaciers, increased runoff, and this increased runoff is also a proxy for increased hydrological connectivity. Now, this can be perpetuated further north into those massive rivers of Siberia. Now, this in turn increases fluvial discharge and increases discharge of fresh water into the Arctic. Now, when that happens, the salinity of the Arctic waters decreases. This increases the sea ice cover and starts to trigger colder glacial conditions. And this is a situation whereby Central Asia and Central Eurasia in particular plays a really important role in driving the Northern Hemisphere climate. So during our field reconnaissance in Kazakhstan, we identified a promising sequence which we thought might provide us with one of these key terrestrial links for understanding the climate system. So this is Sharon Canyon. This is also in southeastern Kazakhstan, and it's sometimes called the Grand Canyon of Central Asia because it's enormous. My postdoc Charlotte Prudhomme, who is now at the University of Lausanne, was investigating records of moisture in Central Asia based on stable carbon and oxygen isotopes. So it's an interesting record because the sediment here records a long-term process of aridification. At the base, we've got about 20 meters of fluvial gravels, which is overlain by about 35 meters of interbedded aeolian and alluvial fans. And then the uppermost 20 meters is entirely aeolian. Now, we worked with a paleomagnetist, Giancarlo Scardia, and we also worked with the University of Frankfurt to undertake some uranium lead dating of crystals within the pedogenic carbonates. And we found that the sequence actually spans about 5 million years. So the entire Pleistocene, more or less. And this is a period which oversaw the beginning of the glacial interglacial phases of the Quaternary that we know. So what Charlotte did was look at stable carbon and oxygen isotopes in the pedogenic carbonates, and she used the delta 13C as a proxy for soil moisture. In addition, she undertook some clumped isotope measurements to give representative paleotemperatures, and this also showed us that the delta 18O is actually a mixed moisture and temperature signal, can't be used as an absolute proxy as such. Now, what we then did was compare our site with a site near the Arctic from the marine records to test our hypothesis about the link between Eurasia and the Arctic and North Atlantic Oceans. Now, what we do see from the delta 13C carbon is that aridification, although we can see it in the sediments, it's not a linear process. We do actually have some ups and downs. But I'd like to just focus on a particularly interesting time period. So the early Pliocene, so 4.5 to 3.3 million years ago. So what we observe here is relatively wet conditions. So what we propose is happening here is what I put forward in the hypothesis before. So we're following amplification of the North Atlantic current. So this is something which happened around about this time because we started to have the shoaling of the Panama Isthmus. We started to get a dominance of westerly transfer, and we had a relatively weak Siberian high. What this meant was that we had relatively effective moisture transport to arid Central Asia. So this increased rainfall and runoff is what we observe at Sharon Canyon. And we see that as a proxy for fluvial discharge in the Siberian rivers just to the north of our site. And what this would have done was, over time, trip a tipping point and result in increased sea ice volume. Now, what this meant potentially, if this happened, was that possibly we're seeing a terrestrial tipping point for the first major global glaciation at 3.3 million years. So the take-home message from this is that it looks like the response of the Earth's surface to long-term climate change in Central Asia is actually generating terrestrial feedbacks, which affected the ocean in the atmospheric circulation, at least on the hemispheric scale. Now, this is quite important because what we understand about past climates is mostly coming from the oceans and the ice cores. But what we see here is that actually what is happening on land is providing really important feedbacks. So it's this is the first paper to come out, which is focusing on this sort of problem, but we have a number of additional studies which are looking at this, the influence of Central Eurasia on Northern Hemisphere climate. So again, all I can say is watch this space. So take-home messages. We've got a bunch of really cool new toolkits for terrestrial sediments, and we can get data from transported sediments, which gives us information about Earth's surface processes and the reconstruction of sediment trajectories and their relationship to climate circulation. Now, looking at in situ sediments, looking at biochemistry and biogeochemistry, we can start to get quantitative estimates of past temperature and precipitation, which provides us also with the missing terrestrial link for global circulation of climate over long timescales. With that, I'd like to thank my research group, which has now been dispersed to various parts of Europe mostly, and also for my colleagues in Central Asia, in Kazakhstan and Tajikistan in particular, for their intrepid fieldwork on the abseil and their excellent collaborations and excellent science in the lab, as well as our many cooperation partners elsewhere around the world. So thank you, and I invite comments.
Thank you, Catherine. Wow, this was amazing. Summing up how many years of work. Wow.
Yeah, it's fun putting it all together and seeing how it fits.
No, it's great. There's great things coming out of that research. It's really cool. So if there are any questions, just unmute yourself and go ahead, please. Okay, then perhaps I will start. I was fascinated by the second topic that you talked about, that you begin to see a way to find out where the loss actually came from by using the ESR method and this E prime signal. And you said what you can differentiate is the age of the original rock. How big of an age difference do you think you need to see that? Can you like distinguish Devonian from Carboniferous rocks, or is it rather like Tertiary versus Triassic, or?
Well, I mean, at this stage, I think what are we looking at in the Kazakh Tian Shan? We're looking at Paleozoic rocks, no?
Yeah.
And then the Zarafshan is, what is that? Cretaceous? Mesozoic anyway. I mean, we could see a very clear difference there.
Yeah.
I don't, at this stage, we're still unclear how much of a role metamorphosis and seismic activity might have on the signal. Mm-hmm. And that's going to actually form the subject of Aditi's postdoc when she goes to Romania in a few months. So yeah, what we're now doing is getting hold of primary rocks and seeing what the signal is there, and understanding also the history of those rocks as well, you know, in terms of metamorphism and tectonic activity. So yeah, at this stage, we don't know. But it's showing promise, and we'll keep going along this track, I think.
Yeah, it would be a great tool, huh? I mean, if
Yeah.
wonderful. So many options.
Especially since quartz is absolutely everywhere. We're not reliant on, you know, small amounts of zircons or whatever.
Yeah. Wow.
Yeah.
Cool. Great. Good luck. Keep us updated, please.
Will do.
More questions from the audience, perhaps.
I think Mark has a question.
Oh, yes, sure. Mark.
Hi, thanks, Catherine. It was very nice. Have you tried to correlate the signal you see with the bulk geochemistry of the dust, for example, to see if there was a difference between the two sites?
With bulk geochemistry, not in a systematic way, no. I have been working with some Chinese colleagues who have been looking at bulk geochemistry from, well, we were looking at Kazakhlos and Ili Basinless in Xinjiang in China, and that was with bulk elemental analysis. What we did find was that the further west you go, the further out into the open basin you go, the more input from the Kazakh deserts and from the Kazakh part of the Tian Shan. That's not a huge surprise, I guess. And I think what it also, in my mind, sort of suggests is that we really do need to be careful about which sites we choose if we're wanting to reconstruct climate. Because if everything is local in Xinjiang, you might have these really spectacular deposits, but they're not necessarily telling us about massive, large-scale climate circulation. Rather, they're telling us about local katabatic winds or something. Yeah, I went off on a tangent there. I guess in short, with the Kazakh samples, we've done a little bit of work, but not in a systematic way. What we're doing at the moment is actually radiogenic isotope measurements. So looking at strontium and neodymium on the same samples. And yeah, maybe longer term, we can take a look at the geochemistry.
Okay.
I didn't have that possibility to do the analysis in Mainz, to be quite honest, and I do here. So
okay, perfect. Thank you.
Thanks for the question. Are there more questions or comments? And I have another one, perhaps, concerning this GIS analysis of the geometry of these dune fields south of Balkhash. Is this something that we know from other areas in the world? Like the geometry that you observed there?
Yeah, so what Maike was doing was looking just at orientation. Mm-hmm. And she was working with various formulae, looking at and at the wind strength and the wind direction, and mm-hmm. what the likelihood of a particular orientation was going to be. And she explored that further in her thesis. So in the paper which I cited in this talk was really the first step, and she took it a lot further. So it does look like actually the orientation diverges somewhat from the present day. So very likely these things are a little bit older. The formation of these things is a little bit older. And yeah, I think we do in the Aeolian dune world. There are a lot of people who work on, the orientation of dunes and what these can tell us about wind transport. Yeah, I mean, it's very early stages in merging two different subdisciplines, really. It's not something that has been done very much, which I'm a bit surprised about, but yeah, it will increasingly be done.
Cool, thank you.
With which, yeah, that's one of the reasons why I have this new postdoc. Advertisement.
Excellent. Are there more questions? More comments? Anyone? Doesn't seem to be the case. So I just quickly post the link to this conference, to the Tectonics conference that I mentioned at the very beginning. If people are perhaps interested to join some active tectonic science in southern France, Catherine, would perhaps also be cool for you to be there.
I'd love to go.
Not lose contact with the tectonics community.
No, not at all. Yeah.
Great. Then thank you very much again, Catherine. It was wonderful. I learned a lot. I mean, it's very far from what I used to do. So it's really cool to get these new insights from someone who's an expert. It's really amazing.
Thanks
Yeah.
for the
So thanks everyone. I'll upload this video to our YouTube channel where you can also find all the previous talks of our webinar series, and we'll keep you informed about the next talk. So thanks everyone for attending. Thanks, Catherine, for the great talk. Stay safe and see you soon. Goodbye.
Kia kaha.